Allora, è un grande piacere avere qui con noi Cecilia Mascolo. Cecilia è Professor of Mobile System nel Dipartimento di Computer Science e Technology dell'Università di Cambridge e in questa università dirige il Mobile System Research Laboratory e il Center for Mobile Wearable System and Augmented Intelligence. Ha coperto anche il ruolo di Deputy Head del Dipartimento negli anni 2018-2021 e ritengo che sia un eccellente rappresentante della folta schiera di italiani che all'estero hanno fatto una grande carriera e che avremo tanto piacere se prima o poi volessero o potessero tornare in Italia. È fellow dello Jesus College Cambridge e nel 2019 ha vinto un prestigioso ERC Advanced Research Grant con il progetto EAR Audio Based Mobile Health Diagnostics. Ha iniziato la sua carriera con un PhD all'Università di Bologna nel 2021 e poi, prima di spostarsi a Cambridge nel 2008, è stato un faculty member nel Department of Computer Science dell'University College London. I principali focus della ricerca di Cecilia sono i mobile systems e le tecnologie di machine learning per mobile e wearable health. Ha un eccellente numero di lavori scientifici pubblicati su conferenze e riviste di altissimo livello con un impressionante numero di citazioni. Ho visto che hai 25K e H-index 79 che sono veramente impressing. Ovviamente è persona di riferimento nell'organizzazione di eventi scientifici del settore ed ha una solidissima esperienza progettuale. Oggi ci presenterà le sue più recenti esperienze nel settore dei wearable device nel contesto delle applicazioni per la salute, un tema di ricerca di forte interesse anche per il nostro istituto, quindi ci sarà una bella intersezione. Il titolo del talk è Wearable Data for Health, Are We There Yet? E quindi Cecilia, il podio virtuale è tuo, puoi partire.
Grazie mille, faccio una prefazione in italiano, poi cambio con l'inglese perché i lucidi sono in inglese e mi confondo, mi dispiace per quello, ma rimango fondamentalmente italiana. Vorrei correggere che purtroppo il mio PhD non è del 2021, ma del 2001.
No,
Mi
no,
piacerebbe avere il PhD del 2021.
sbagliato a leggere.
Grazie, ti ringrazio per questo. Anyway, I'm going to switch to English. I'm sorry not to be there in person. I was traveling last week. I will be traveling next week. I like to come to Italy, but not this week. All right, so this talk is about wearable devices, which are generally quite pervasive. We wear them a lot. I wear them while I talk to you. I also wear them while I talk to you, but I also wear this device while I go running. And so the power of this device is to be scalable technology to understand how our behavior and health is very wide. However, as a researcher, I also like that there are still limitations and challenges that we can tackle to try to make this technology better. And I will list some of them and give you some examples of them and see how far we get with the time we have. So the first thing I want to talk about is the fact that we think, or at least we know, that these devices can be inaccurate, especially when we move. Some of these sensors, such as the PPG, which is the light behind this wearable here, when we move our arm, because we wear it like this, and we go running, the arm moves a lot, and therefore the precision of the heart rate monitoring that can be done through the PPG sensor can be affected. And so this is an example of a user that was complaining. It was comparing a ground truth device and another watch device and showing that the measurements of the heart rate were different. So people are noticing these things. So there's a realm of work that can happen in improving the sensing of these devices. However, I also want to realize that I want to make you realize that if we start considering longitudinal data, perhaps some corrections are possible that might correct the algorithms without correcting the sensor processing itself or the sensor positioning itself. We have a lot of data about the stream, and therefore, perhaps by using and leveraging the information that we have in this, we can say a lot more. And we don't need to make the sensor more precise. Also, in some cases, the precision of the sensor might not be what we need. It might be enough to have enough longitudinal data rather than one single point. And for this, I want to give you a soft example. So this is how sleep is monitored. This is called polysomnography. you're put in a lab, in a bed, where you are strapped with all sorts of respiratory ECG sensors, nose sensors, heart rate sensors, anything you can think of, and you are supposed to sleep. This is done to understand perhaps why you're not sleeping well, if there are some inherent pathologies that affect your sleep. However, no one can sleep well in this setting, it's well known. However, still, this is the gold standard of how you monitor sleep. And also, this is not very scalable because you can't do it for more than a couple of nights. You can't do it for the whole population. There are limits of this technology, but yet this is the gold standard on how you realize if someone is sleeping well. And so in 2021, and this is just one example of the many papers that are starting to come up saying, well, with respect to polysonography, which is this example that I've just shown you, so the gold standard of sleep monitoring, the consumer-grade sleep trackers, such as the wearable devices, Fitbit, and what equivalent, are not good enough. And so, there are all these tables showing the errors, especially in sleep phase monitoring, that show that the technology has errors with respect to polysonography. However, one thing that perhaps we are not considering is that in some cases, the technology is needed to understand things that do not need the level of error that polysonography can give you, but the error that the sleep tracker gives you is good enough. And so I think it's important as researchers that we remember what our goal is and what kind of error is needed to solve that problem, and perhaps how we can proxy those limitations of a sensor, maybe considering that we might have more data with errors. So I have years of data of my heart rate while I sleep from this now, while I could have one night of polysonography. Which one is more valuable despite the errors? These are questions that the community needs to start asking themselves. And I like the screenshot. So this is a Sleep Cycle app, and this is on their website. They have every week they change, but this is one I took a few months ago. So these are the sleep statistics of the week of different countries, right? So this is an app that runs just on the phone. Now they have a watch version, but this was run just on their phones, and they measured things that they use a microphone, but also without the microphone, information about when people use their phone in the morning and in the evening. So they know how much roughly people sleep just because of the interaction on the phone. And out of this very granular information, they make statistics. Statistics are important for public health at a very high level scale. I want to see any polysonography study being able to have this sort of very high level statistics. And so I deliberately took a sensor that was very coarse-grained and very inaccurate and very imprecise, but had a reach of a scalable set of population in all the countries. And this, to me, is the opposite of what polysonography is. So in the middle of this, you have a solution with sensors that can give a realm of measurements that could be useful in very many ways, and very, very fine-grained data, even if not precise, even if not labeled. And on this aspect of labels, I want to drill more. When you start trying to collect data from wearable devices, it is very hard to have labeled data. You can perhaps tell me in a scripting way. Sometimes we do it for studies. I take a bunch of PhD students and I say, okay, well, now you all wear this device and you go up and down the stairs and we get the data of that. Start now. This is the synchronization time. You go up and then you go down and you do 5 jumps and you run around the room. And we have all this data and we have reasonably good labels. But how much can I do of that? And how many people can I force to do this with? Obviously, this is very limited. So the new domain of machine learning is working with unlabeled data. We're seeing these new technologies, new techniques starting to develop, especially for imaging and large data sets of that. And we have worked on applying this sort of technologies also to data that comes from wearable. And so in the next 2 slides, which are quite dense, but don't be scared. I'll go very slowly, and I'll give you the high level aspects of it. I try to describe a technique that we have developed that works with large unlabeled data sets for activity recognition, and trying to leverage the information that we have on unlabeled data to then be able to have a model that understands activity recognitions with very little labeled data, a lot of unlabeled data, and do well on activity recognition tasks. And so this model is one example of self-training, as we call it. The model is using, for those more inclined to machine learning model, you might have heard of teacher-student models, and this is exactly what this is. The next two slides are splitting this very difficult graph in the top part and the bottom part. So you will see the next graph will have the top part, and we'll go through the high-level concept of what this is, and then we'll go to the bottom. So the top-level part, the first thing we do is something very traditional that we've always done in machine learning. We have some label activity recognition data. Perhaps we go back to the data that I've collected with my students, telling them to go up and down the stairs. So I know the labels of that data on the watch. And then we use that, we have the labels, we split this data set and in testing and training data set. We'll keep the yellow bit, so the testing set, we'll keep it aside. I'll talk about this later. We take the part of the training and build a model, which is a deep neural network model, CNN in particular, to feed this data in and train this model. Notice this is not much data. So there's nothing new here. So until here, it's something that you should know very well. We take the data, we train the model. But then we do something else. We take a large unlabeled data set. Our colleagues in the School of Epidemiology have been very wise, and about 5 to 10 years ago, they put wearable devices on their population of genetic studies. And for 1 week, a bunch of individuals, thousands of individuals, has worn an activity sensor, an accelerometer. So there's a large data set there with no labels whatsoever. What do we do with it? We pass it into this model. So now we have the model is trained with this labeled data. We pass the large unlabeled data set onto this model and generate something like an output that says this particular piece of data is recognized as activity, I don't know, running. But we don't have the label for that. And so we have an additional step that says, depending on the confidence on the model, so the level of probability, the classifier is all probabilistic, so we have a probability there. We decide on a threshold, and this aspect I don't want to describe, but the ones on which the model is more confident, the labels on which the model is more confident is kept, and the ones that are less confident is left aside. So now we have silver standard labels on a data set that was unlabeled, but it's a lot of them because this data set was very big. And we didn't have labels, and now we have something on which we have reasonable confidence that is good data, good labels, but it's not something we are sure about. What do we do with that? We do an additional step where we also start creating augmentations of that data. So the data is now augmented by rotating it, turning it, scaling it. So having some sort of augmentation so that out of the original data, which was already a lot, we have even more data. But we know what kind of augmentations we do. Here are examples of noise, negation, and flipping on the data. And so we have now an augmented data set on which we know labels that are A, the confidence label that we have out there. I think this is running, and I have good confidence that this is running. And then we have, oh, this data has been, is data running, but some noise has been added, or this data is running, but it's negation of the running. So it's negation of the data. And we build another model that is a multitask model that is able to take a data set, a piece of data, and decide if that was a piece of data on which noise was added, or the data was flipped, or the data was negated. So the model, by running this task is learning something about the data, how this sort of HAR data is looking like. There's also an additional task, which is the task of recognizing the activity. By doing all of this, what we are intuitively doing, we are making the model learn things about the data, different things about the data with a lot of data, which we didn't have at the beginning. We only had the small data set. Now, our aim is to essentially say that when you then do the activity recognition, so if you then in the end only consider this task and consider this sort of network just for the HAR task, and you try to feed the testing data we had at the beginning. I'm going back one slide for you. So at the beginning, if you remember, we had all of the data, we split it in training and testing, and we kept this yellow bit aside. No one has ever seen that data there. And we use it here to prove that the model that we built, which is a model built by leveraging large proportions of unlabeled data, works better than a model that only uses labeled data, smaller labeled data. And so this is a way in which the community is moving away from labels, or at least trying to become smart in the way we move away from label. We have used augmentation to augment the data, and we have used this smart technique to label some of the unlabeled data. And so this is one of the examples. If you want to read more about this paper and the results, there's a reference here, which is also on my webpage. I also want to move on another really beautiful things about wearable data, which is that it can bring us beyond the sleeping lab or any sort of task that require unscalable tests. And to give you an example, I want to talk about cardiorespiratory fitness. Cardiorespiratory fitness is a very good indicator of your cardiovascular health. It's a better indicator than smoking, cholesterol, hypertension, and diabetes. So it's a very good thing to have. Problem is, measuring your cardiorespiratory fitness is cumbersome. And so here in the picture, if I was in the room, I would ask you to raise your hand to tell me if you have done one of these tests. And usually I would tell you, well, you're probably very athletic, very fit if you've done one of these tests, because people that do these tests are usually people that tend to run marathon or have interest in athletics activities. This test puts you into a room where there's a treadmill or a bike, then there is this mask. The mask is there to measure your VO2 max, which is your volume of oxygen that you breathe in, and then is transported in the blood to your muscles to be then transformed into energy. And this measure is a good proxy of your cardiorespiratory fitness. Problem is, it's very unscalable as a measure. And also, for those who have done this test, they would know that it's a very strenuous activity. And so perhaps on the population where you really want to measure cardiorespiratory fitness, those that can be unfit, this is not a good way of doing it. And so wearables could be a good proxy of it. And some of you probably have an Apple Watch, and the Apple Watch is actually giving you an indication of VO2 max. But actually, the way in which they measure it is very obscure. We don't know the algorithm. And two, we suspect they only measure it for when you do vigorous activity, which means for the majority of the population, this is something that is not done. The open studies have always done with very small data sets. So what we've done is to take a large data set of, this is data that the epidemiologists have collected in 5 years, and they have collected a population of 11,000 people, and 7 years later, another 2,000 people, the same that they were here, were then re-monitored. What did they monitor on these people? These people had all sorts of ages and conditions. So they had all the genetics, they had all the diseases tracked, but they also measured, they also measured the VO2 max. Now, they had put people on the treadmill, but being them epidemiologists and knowing what they were doing, they also put people on the treadmill that had a certain age and certain cardiological risk, allowing them to run to not to their extreme, but a bit earlier than the extreme, and they have a way to extrapolate what it would be at the extreme. So there is a way in which they They don't have gold standard measures of VO2 max, but they have an approximation of that. So you could do it in theory on a treadmill. But however, this remains very unscalable. It's good to have different ways of considering that. They also had anthropometric measures, their questionnaires, but most importantly, they asked everyone to wear an accelerometer as well as a chest strap for detecting movement and heart rate. And this was done for 6 days. So we only have 1 week of data for each participant on this data set. And what we've done here is that we've done something really simple. But the idea is, can we, from this data, predict VO2 max in large scale? And so if you take the accelerometer data, you take the heart data, you calculate features. So we've done feature extraction here, and we used a simple, fully connected neural network to then detect the fitness. So can we predict VO2 max out of this data? And the results, again, if you want to read the details, this is just a keynote, so I won't spend too much time on this. The results show that if you, let's look at this picture essentially only, but we make some mistakes, but generally we are quite good at predicting the VO2 max. There are some differences here and some differences here, but generally the approach works quite well. And the wearables add additional improvement with respect to resting heart rate, which is something that you can measure even just by counting, staying still and measuring, counting your heart rate from the pulse on your arm. You don't need a wearable for that. And the anthropometric measure, the fact age, sex and weight and BMI are very important predictor. But even the wearable add a little bit. And sometimes even the small error correction is very important. So this leads to, it's a good way to start showing that we have good proxies for this sort of issues. But for computer scientists, I think this part is actually more interesting. So here is the same data, but for this we have devised a sort of pretest task, a task that we do just to find out something else. So here the task is that we take the accelerometer data of the same people, and we try to predict heart rate. And then your question would be, well, why are you trying to predict heart rate? You just told me you have this heart rate measure. I showed you in this picture, we have the heart rate measure, right? So that's why I said this is a pretest task. It's a task that we do to do something else. So can we from heart rate predict heart? Can we from acceleration predict heart rate? Yes, we know we can. I mean, this is a well-known fact. There are high correlations between the way you move and your heart rate, and this can be found. So the prediction task is one that we know. However, we wanted to see what the network learns while trying to do this task. And it turns out, as we know, as we learn about deep learning networks, that the network is learning a lot more about us than just the heart rate from the accelerometer. And so here, we have a normal convolutional neural network followed by a GRU just to consider the temporal components of the accelerometer data. And with this network, we predict the heart rate. We take the embeddings of one of the last layers here before the prediction task and use these embeddings into, we do a principal component analysis to reduce them, and then we use them in a linear model. I mean, it's a classifier that can predict something else. And what are we trying to predict here? Well, we try to predict BMI, we try to predict sex, age, energy expenditure. These are things that we know were also in the data. So we have the ground truths, like these anthropometric measures we have in the data. And so we're trying to say, can we, from accelerometer, deduce this data while we try to learn something else? Can the network learn other things about us? And this to me this is a paper we published in 2021, and it's quite interesting. And this is a keynote, so I can talk about other things that are not just mine. And related to that, then now in 2024, a paper from Apple was pushed out from one of the main machine learning conference, ICLR, where they used their own signal processing techniques, signal processing data of lots and lots of participants, and they built a foundation model that learns from all of that data with pretext task. But the the model is so good at that point that is able to be applied on downstream tasks, like we have done in the previous paper, to learn other things about the users in the same way. So what am I saying here? I'm saying that this data is very rich, and we're starting to recognize that this data can lead to downstream tasks that are perhaps beyond what the aim of the data collection is. So this is a very powerful, and I recommend if you're interested in foundation models that you read this. Generally, foundation models recently had a lot of attention in terms of LLMs, but this is not about LLMs. It's about different starting data. And so I will switch gear a little and give you another example of a sensor on which we have done some work, and again lead to possible foundation model ideas. And this is the microphone. The microphone is very powerful sensor and can scale up quite considerably because it's cheap. It can be put in other devices, and most importantly, again, it can give a quite granular data about us. It could listen to us all the time because it can be with us for quite a while. And so during COVID, with a team of colleagues that are working in different disciplines, we released an app that collected microphone data of people. And in this screenshot, you can see what the app collected in addition to demographics and other more traditional things such as symptoms. They also asked people to breathe, to cough, and to read a sentence on the screen. And this was to try to see if voice and cough could be indicative of disease. In particular, the only disease that was out for a certain period of time in our past is actually COVID. So could we predict COVID? When we're trying to study this problem, other researchers, these are two papers published at the time by CMU, also noticed that because this was a lower respiratory tract infection at the time, you remember when it was really hitting our lungs, then the voice was very affected, and affected in a way that was very different from any other respiratory infection. Then the disease, of course, moved into mutated in something completely different that couldn't be distinguished from other things. That it's actually quite important to realize the power of these things at the time. So we have a portion of the data where I think the possibilities were very powerful in this sense. How did we, for those, again, more machine learning inclined, we use cough, breathing, and voice to feed into a pre-trained CNN model, a VGG model, and then consider the features that came out of that to be used in a connected set of layers to then diagnose both a single point diagnose, but also longitudinal diagnose if we had more data about a single user. Performance and limitations of the approach are in the paper over there. I won't talk more about this except showing you the implications of this work. First one is that I could have been very rich. At the time, Pfizer bought an app that was built in Australia for 150 million, and it was doing roughly the same thing. I'm downplaying it. Actually, the ResHub people have been working on this sort of problems much longer than we have, but it's very interesting. Technology is now taking up in this sort of area, and people have started understanding that voice is a very good marker of disease, and one of which we can get a lot of information on. What we are doing right now is doing the same thing we've done for that Apple has done for the markers, the PPG and ECG data that they had. We had tried to build a respiratory acoustic foundation model. This is something that we have just sent to a conference, but I wanted to lead you to this just to give you an example of the power of this data. So we have our data set and a number of other data sets that are being collected about respiration diseases. So some are general COVID cough, others are more general about lung sounds, collected with stethoscopes even, so not just with the microphone. And we have a number of tasks that are downstream tasks on which we try to predict. The result of all this is that a model that learns from a set of data that is diverse is able to do better than a model that is trained on a smaller data set and specific for the task. That's one of the important findings of this work, and we're still working in this area. It's a new direction that we are taking, but I always try to give people the latest things we're doing because they are the most interesting. We are also looking at longitudinal data, audio data. There's very little of that. The previous data was, the COVID data was also trying to predict based on one single cough or something. But if you start having data about people improving in their COVID trajectory or getting worse, then it's interesting to see if we can predict the trajectory of a disease. And this is very important generally for respiratory tract infection. And so now we have a big project trying to get people to tell us when they go to the doctor and get antibiotics, and we try to see if their respiratory tract infection are getting worse or getting better. This is a very big area of research. I think I'll take another 5 minutes to talk about privacy work, but then I'll take some questions. So obviously, when you talk about all this data, this is very, very sensitive data. And so the idea that it all goes back to the server to improve the models is like, might not be the best way. The best way might be that we try to build a model, maybe collecting some of the data, but then we quantize the model and we try to reduce it so that it can run on device. And I work quite a bit on the area. I have a few more slides, but I think I will only give you this slide and maybe you can ask me some questions after that. So we have two works that work on this. One is about trying to make continual learning, which is very important when you talk about mobile and wearable devices because your environment changes quite a bit. The users change. And you can't predict that when you set up the model at the start. And the idea of retraining in a small device is very energy consuming. So we are trying to bring continual learning on device on very small devices, considering MCU as well. And the latest work is also trying to train a model on device. We are not training the full network. We are being smart in which part of the model we can train on the device, and you can read more about it. It's on all of this is on my webpage. You can find the PDFs. I will, I think, stop here and start taking some questions instead of presenting the details of one of the approaches that I had, because I think I told you enough. So please let me know if you have questions now. Thank you very much.
Thanks a lot, Cecilia. Do we have a question from the audience? Vieni qui, Sara.
Oh, okay. I think this is working also.
Yeah.
Can you hear me?
I'm okay with questions in Italian too.
Okay. As you prefer, but I think that we have someone speaking in English in the audience, so we can go forth in English. So thank you very much, Cecilia, for the presentation, which is really, really interesting. Actually, also at Isti and different labs, we work in similar kind of research activities and topics. Actually, you talked a lot about large data sets. I was wondering whether these data sets are freely available or are private data sets that you have the lucky to use for developing your models.
Thank you very much. I think this is a very good question. So the first data set, the Finland one, is one that the epidemiologist has given to a number of people, but we have gotten it from them. So I am not sure how they're sharing. I think they're still, I think they're publicly sharing, but I don't know their processes externally to Cambridge. So that's one. The second one, and I'm going back to that slide, all of the data sets we have used here, this model, which I haven't given you the link because we still have to put it on archive, but it will be on archive very soon. Those are public. This is our data set, the one I've talked about, and we have released it as a controlled access data set. This is because it contains voices. And so the way you get the data is that you send me an email or go on the page of the project and send an email to that link. And I send you an agreement that your department or university need to sign. And then we share the data with you when you've signed the agreement. The other data sets indicated here, I think are all publicly available on the web. or at least have some similar agreement. So this can be reached. I think in general, the availability of data is an important thing in wearable, but if we can start putting together data sets that exist, even if they're small scale, and build better model, there are many even smaller scale HAR data set collections, and some more can be detected, especially if you don't need perhaps labels like I've mentioned before. But that's a very good question.
Yes, indeed, because this is one of the long-lasting issues now when you try to train these models and develop some really effective solutions. And another question, I will go and read your papers for sure, but so that's why I'm asking very high-level question. The other question is about how did you get, I mean, which kind of feedback did you get from clinical people that should use the output of your models?
That's a very interesting question. So at the time of COVID, everyone was sitting at home, apart from the doctors, and the doctors were really interested in this, and they sent me an email. The ones working in the wards, they were saying, okay, we can hear the disease. I think I know your model works because I can hear it. And we did a test. We recruited 23 clinicians in different levels of their training, and we sent them the samples, and we knew the label because the user sent us the testing, the test data. So we knew if it was COVID or non-COVID. And we asked them to listen and to tell us if they could distinguish if the user was healthy or COVID. And what we found is that in some cases, the model was better than them, but in some cases, the doctors were better than them. And this often coincided with the doctors being in a COVID ward. If they were in a COVID ward, they were really, really good, and the model couldn't generally beat them. But if they were just generalists, then they weren't as good as the model, which tells me, as usual, when we have very, very trained clinicians, they are better than the AI, but in average, they might not be. And we've seen it for other papers. And so this is very interesting. And I think this discussion of how is the AI helping the medical profession is a very interesting discussion that should be kept going.
Thank you, Ceci.
Following Sarah's question, have you tried also to compare the results of this test based on audio with other investigation techniques like X-ray? What is the relation between two different ways of detecting an illness?
We have not, because we didn't have X-ray of these people, and we have not done a study on that. I imagine X-ray is very powerful, and this technique is very inaccurate. I can already tell you that. But how many people can afford to get an X-ray done, and how many times can you get an X-ray done? So this technology has the potential to give you a longitudinal feedback every day. You could get a feedback, be reassured that your infection is getting better, that you don't need antibiotics, you don't need to run to the GP. The X-ray machine, although they're getting more portable, are not yet there. So I think they're quite compatible. On the clinical study that I was mentioning in the previous question, I want to say that is also on my webpage. We published that, so you can read about it. I haven't put slides on it, but yeah, you can find it.
Yes, thanks, Cecilia, for your talk. This was very interesting and also very clear for me. Well, concerning the graph about VO2 max, I have a question for you. My question is about the very different conditions between VO2 tests done in a lab setting with respect to data collected from a smartwatch. I did VO2 test a couple of times, but I did many times FTP test or 5K running test and many others. And according to my experience, you have to train yourself before being able to complete a successful test. In other words, it is important to train how to complete a test. From the data, from the results you presented us, you take this data and you run some prediction algorithm. So my question is, who is the target of this prediction? Do you think a sport specialist can use these results to train or to, I don't know, work to prepare athletes? Or these results are mainly for a sort of sport amateur that do not have specific requirements. So it's a question about the target of this analysis.
Thank you. So the target is the general population. It is not the athletes. The athletes probably are already going on VO2 max test every year, and they know how to do it, and they can run to the extreme. They can afford to do it. So those are the ones that, yes, they can use the technology. It benefits them because they might have a finer granularity. They can have a response over time. I certainly use my Apple Watch to see my performance. These are for the general population. Now, in terms of the VO2 max tests run to collect this data, the epidemiologists know what they're doing. So I imagine, I haven't asked them specific questions about this, but I imagine they prepared their participants to collect the ground truth data very well. And as I said, they don't run participants over 60 or 65 to their limit. They know, maybe based on the resting heart rate, how much they can push them, so that they can then project the rest of the VO2 max component. They have formulas to do that. That's in one of their papers. And so really, I think this technology, our study is really about population health. It's about cardiorespiratory fitness of the population when you can't get this test done. Yeah, so if you need more precision, I think on athletes, you do need more precision. And I don't know if this technology is yet precise enough to give you the level of change that that is necessary for an athlete to understand if they're really improving their VO2 max. But I might be wrong. I've not done enough. We're doing quite a bit of that now from wearables, trying to understand if you can get that from wearables. And that is mainly for athletics.
Thank you.
Any other question? Okay, in this case, Cecilia, I will like to say you again thanks for being with us today and for this inspiring talk. And I again tell you that we will be pleased to have you in Pisa whenever you want, visiting us. Okay.
You're very generous. I hope to visit. I do like Tuscany, so rather than going to Emilia-Romagna, which is always either very hot or very cold, I will come to Tuscany. So thank you again. Have a good day. Bye-bye.
Bye-bye.